Okay, I think some of us still are joining. So you are having a class?
Yes, sir.
We
Which
had
course?
one till
Which
11.
which class?
Solid mechanics.
Okay, who is teaching this course? Professor Chaudhary?
Yes, Sandeep sir.
Okay, okay, good. Okay, I think we can start. So in the last class, we were discussing how you can analyze a fluid when this is under the motion. And that is the dynamics of the fluid. And for that purpose, we said, let us consider a stream line. So here I have a steady flow situation. So this is a steady flow situation, and this is a streamline. So steady flow along the streamline. Now this direction is x, another is y, a streamline direction is s, corresponding perpendicular direction is n. So let us consider a small part of fluid in this region. So we will consider the forces that is acting on this fluid. So weight is acting, that is in the downward direction, and let us say this distance or length is ds. So chord length is, and this side area, this area is dA. So this area is dA, and this angle, let us call this angle is theta. So the angle is theta. At this point pressure is P, so one force, so let us call pressure at this point is P. So one force will be acting in this direction on in this elemental area, and this will be P times dA, P times A. So this side force acting is P times A. You have another force that is acting in this direction, and that is because our pressure this side will be increasing. So this is P plus dP at times dA, that is your force at this point. So pressure is P plus dP, and at this point let's call pressure is P. So we can write an equation. So if I consider this motion of any fluid particle, the velocity of the fluid particle will be function of two things. One is s, and this is also a function of time, because at any point the velocity can change with time. So velocity has a function of time as well as also a spatial coordinate. In this case, the location is s. So we can write dv is equals to, if I expand this, then I can first differentiate partially with respect to s, multiply by a small distance delta s. In this case I am writing ds del b over del t, and this is multiplied by dt. So if you divide both sides, or you can say you can or you can take dt this side, basically it will be divided by delta t, and then you have to take the limit. So this is dv by dt, this will be dv by ds multiplied by ds by dt plus del b over del t, and this dt goes. Now if you have a steady flow, so which term will be zero in case of a steady flow? Which term will
Del
be
V by
zero?
del T will be 0.
Okay,
Yes, sir.
so good. So this is a steady flow. So if I have a steady flow, so for a steady flow, we can have this term is equals to 0. So in that case, we can write velocity is simply a function of a spatial coordinate s. So v is equals to V is simply a function of s. And if I want to calculate acceleration, then in that case as is equals to del v over del s, because this is nothing but acceleration. So acceleration is equals to dv del v over del s multiplied by ds by dt, because other term in this case is 0. So now we can write acceleration in the s direction is equals to del v over del s, and ds by dt is simply v. So we can write here acceleration in the s direction is equals to v times, or since velocity is only function of s, because we have assumed this is a steady flow, then we can simply write this is equals to dv by ds also. So this is also correct because this is only a function of. So we can write acceleration in this case v dv by ds. Now if you consider equilibrium of the elemental area in the s direction, if you remember, what are the forces that is acting? You are having a force P times dA. Earlier I showed you this elemental area. So in this direction you have a force P into dA, and in this direction you have P plus dP times dA. So these are the forces that is acting. And then you will have weight in this direction. This angle is theta. So in this direction you will have W cos theta, and in this direction you will have W sin theta. So this will be minus W sin theta is equals to mass into acceleration, and which is m v dv by ds. Now here you can simplify a little bit. So p dA cancels out, and then you can put all this thing. What is the value of mass? What is the value of weight? Sin theta, and then you can simplify. So let us write mass. Mass will be rho times volume, elemental volume, a small volume. So this means rho times dA is the area. So if you consider this portion, this area is dA, and this length, this side length is ds. So volume will be rho times dA times ds. So this is your volume, and this multiplied by, so mass will be rho times dA times ds. Weight will be mass times z. So this will be rho times dA times ds times z. And sin theta will be, so if you see this, in this case, this angle is theta, and this length is dx, and this length is dz, and this length is ds. You can verify yourself also. So sin theta will be dz by ds. Now if you plug all this, so you will have, first you cancel p times dA, then you will have dp times dA minus w sin theta is equals to mv dv by ds. Now plug yourself the value of m, w and sin theta and give me the final expression that you are getting. So plug the value of all the things, cancels dA, and give me the value, give me the final expression. So what is the final expression after cancelling and putting the values of different terms? Anyone? Am I audible?
Yes, sir.
Okay, so give me the value. What is the final expression? And this is the way of my teaching. Generally, I do some calculation and then I ask so that you are on the track also. Plug the value of Wm and sine theta, cancel different terms and give me the final expression.
Yes, sir.
What is the final expression then? Are you doing or not?
Yes, sir.
So what is this expression? Tell me. Hmm. Okay, Mukesh, tell me what is your expression?
dp by rho plus g ds plus v into dv equals to 0.
Okay, good. So you will get something like this if you plug all this. So minus dp minus rho z dz is equals to rho v times dv. And if you further simplify, you will have minus dp minus rho z dz, and you can write this rho by 2d of vs square because differentiation of vs square is 2vs square, so let us divide by 2. And if you integrate this term, so if you integrate, what I will get? Anyone can guess? What are the final thing like? Is that expression is familiar to you?
Bernoulli equation.
Bernoulli
Yes.
equation.
Good. So if you integrate this, then you will have, if you divide by rho and then integrate, so dp by the same expression minus z dz. So let us this plus here plus 2 half times dv square. And if you integrate this both side, and I'm assuming that dp by rho is like a incompressible fluid. So rho is constant. That's why we can take rho outside. And if rho is not constant, then you have to write rho as a function and then you have to integrate. Otherwise, you can take rho outside and simply you can write dp is equals to p. So if rho is not constant, then you have to keep like this. Otherwise, you can take outside g times z, and this is, if you put all this side, so this is minus, put all this one side, then you will have zz plus half v square, and this is equals to constant. So along a streamline, you will have this term constant, and if when rho is constant, then you can simply write zz plus half v square. This is equals to constant. So this is your Bernoulli's equation, and this is for a flow, and this we have derived considering the equilibrium along the direction of the streamline. So this is constant, so this value is constant along the direction of the streamline, along the direction of the streamline. So this term will be constant. This means if you want to apply at two locations this equation, if you write at point 1 and at point 2, you can write P1 divided by rho plus ZZ1 plus half V square. V1 square is equals to P2 by rho plus ZZ2 plus half V2 square. So this is the expression you will have if you want to apply. Now this term is, so basically this is nothing but energy conservation. You may have learned in elementary physics also. The same thing you can derive considering the motion equilibrium. And the same thing you can also derive using energy principle. Because these two are the same thing, looking one problem by two different aspects. Either you think in terms of energy, or you write equation of motion. So you will come across the same thing, final conclusion will be same, final result will be same. So this is basically energy, and this energy, different terms in this case are different energy. This is your flow energy. And this term is your potential energy. So potential energy depends upon the reference, potential energy. And this is your kinetic energy, you can say. So this is your kinetic energy. So basically, in other words, we can say sum of the energy is constant along a streamline at two different points. Now we will consider force balance along the tangential direction, or you can say across the streamline. So if you consider force balance across the streamline, simple thing. So if you consider equilibrium across the streamline, this is your streamline, this is the portion that you have. So let us consider this time, this length. So what are the forces that is acting? So this will be elemental volume, in fact. So across this direction I am going. So force acting this case is P, and since I am going in this direction, at this point pressure will be different, that is P plus dP. That is acting in this direction. Other things will be same. So this is weight W, and let us call this area as dA, and this dimension was n dimension. So length in this direction is dn, and then you can also put this theta here. So theta is this angle, the same angle, theta is same angle, so this is theta. So this will be theta, and this is dz, and this is your dx. So you can write, considering the equilibrium in this direction, you will have W cos theta. So if you consider equilibrium across the streamline, you can write P into dA. So this force is acting in this direction, minus P plus dP times dA minus W cos theta, because my positive direction is this direction. That's why W cos theta becomes negative. This is equals to mv square by r. Now from here you can say, so this is your dn in this case. You can write this will be, so what will be the cos theta? I think this will be, this is for the previous case. You will not have this. You can verify yourself what will be the cos theta in this case. So let's say, so what will be the cos theta in terms of dn? So this will be dn divided by dz. So you can show, so this length is dn, so I can show here. So this length is dn, and this angle is theta, and this length is dz, and this length is, so you can write cos theta. So this length is dz. So cos theta is nothing but dn by dz, because this is perpendicular. So cos theta is equals to dn by dz. So this means dn is equals to dz cos theta. So you can plug it here. So PdA cancels out. So you have minus dP times dA minus W cos theta is equals to mv square by r. Mass is known, m is equals to dA, this time length is dn, earlier it was ds, times rho, and w is this times z. So if you plug all this value, rho times z. So if you plug, you will have dp times dA plus w cos theta plus mv square by r is equals to 0. So this is dp times dA plus dA times dn times rho times z times cos theta plus this multiplied by dn times rho times v square by 2. So if you cancel out, you will have dp by rho plus dng cos theta plus dn times v square by r. This is equals to 0. So this is dp by rho plus z dz cos theta. You plug the value of cos theta and then v square by r, dn is equals to 0. Now if you integrate both sides, so integrating, you will have, and we are assuming this rho is constant, in that case this will be p by rho, and this will be simply gz, and this is integral of v square by r dn. This is equals to constant. So this expression you will get, that is considering dynamics or considering equilibrium of fluid particles across the streamline. So this is considering equilibrium across the streamline. Now what if r is equals to very large value, that is if r tends to infinite, in that case this term will be 0. So you will have p by rho plus g by gz is equals to constant. So this is basically flow along a straight line. Because r is infinite, this means this is a straight line. So this is a case of flow along a straight line. So this is a case of flow along a straight line. Now see, in this case, this pressure is only depending upon z plus constant. It's not depending upon velocity or radius of curvature. So this means if we have a fluid that is flowing along a straight line, then this thing will be same as if you have a stationary fluid. What this means, for example, let us consider a stationary fluid. So this fluid is a stationary, this dimension is your z direction, and let us consider this point is point A and this point is somewhere here, this point is B. This is a stationary fluid. And let us say in this case the fluid is flowing. So at this point is C and this point is D. So fluid is flowing in this direction with a constant velocity, because this is all applicable for a steady flow. This is your z direction, so this is flowing fluid. So in this case, if I consider a cross, so this is the direction of flow, so this is a cross direction. So this means difference in pressure between C and D, that is PC minus PD, will be same as PA minus PB, because in this expression you don't have any velocity term. So we can say here that is pressure difference between two equal height points in a stationary fluid and flowing fluid will be same, that is Pb minus Pa is equals to Pd minus Pc. So pressure difference is same. So I can say the variation of pressure with elevation in a steady incompressible flow along a straight line. If the fluid is flowing along a straight line, it's same as is the same as that in the a stationary fluid. A stationary fluid. So we discussed dynamics of a streamline along the of a fluid particles along the streamline and across the streamline. Now you see this Bernoulli's equation has three terms. These three terms you can think of in terms of energy or you can think of in terms of pressure. As I said earlier in elementary physics courses also, you can do the same thing, same objective either considering the energy or considering the forces. Equivalent of force is pressure. So the different terms of Bernoulli's equation, you can either think in terms of pressure or you can think in terms of energy. That's why we also categorize different terms in Bernoulli's equation in terms of pressure. So we'll discuss different types of pressure. So we have a static pressure, dynamic pressure, and a stagnation pressure. So what are these three pressure? So if you see the Bernoulli's equation, if you rewrite in this form of V square Gz, this is equals to constant. Or you can write P plus rho V square by 2 plus rho Gz. This is equals to some constant. Now, this pressure is called a static pressure. So this is your static pressure. So this term is a static pressure. This rho V square by 2 term is dynamic pressure. Dynamic pressure. And this is your, and this depends upon the reference, because where are you choosing your reference line? This is called hydrostatic pressure. Hydrostatic pressure. So same thing, you can either say flow energy, kinetic energy, or potential energy. Now we are calling in terms of pressure. The sum of a static and dynamic pressure is called a stagnation pressure. So these two terms, so sum of these two is called a stagnation pressure. So these two terms, if you combine, this is called a stagnation pressure. So sum of these two terms, static plus dynamic pressure, because this does not depend upon the reference. Basically reference that the hydrostatic pressure can be zero also, because it depends upon the reference line. So this two pressure, static plus dynamic. So we can write P as stagnation. This is equals to P plus rho V square by 2. So this is your stagnation pressure. P plus rho V square by 2. What this means? This means if you want to measure a stagnation pressure, you have to put a tube and so that the velocity suddenly comes to rest. So whatever the force that we have, whatever the pressure that we have, that will try to rise that will rise in the tube. So let us try to consider this. So if I have a fluid that is flowing inside this closed tube, then you can measure the pressure inside this. There are two equipment we are putting inside this equipment that we call a piezometer. So in this case, water is flowing and water will rise up to certain height. Let's call this height is P. So this is your static pressure. So this is so what the piezometer is measuring, this is measuring a static pressure. But in this case, water will rise even more. So this is P that the piezometer will measure, but some more distance. And this will be rho V square by 2. So this distance, this pressure, this is basically your P stagnation. And this is measured using instrument, and this instrument is called P-tot tube. So this instrument is P-tot tube. Why this water level is high? Because at this point velocity of this fluid is 0. So this means velocity is suddenly becoming 0. That's why this will rise even further. So a stagnation pressure is a pressure at a point when the fluid is brought to complete a stop. That is your stagnation pressure. So what is a stagnation pressure? So this is pressure at a point where the fluid is brought to complete a stop. This is your stagnation pressure. So if you know a stagnation pressure and a static pressure, that is P in this case, so this is your stagnation and this is P, a static pressure, then you can calculate the velocity because you know this expression. So you know this term and you know this term, then you can calculate the velocity of the fluid. So if you have two devices, you can calculate the velocity of the fluid. So what will be the velocity? So velocity in that case, if you re-express that expression, you will have 2 times P stagnant minus P divided by rho. So fluid velocity in terms of a stagnant pressure, and this P is the static pressure. So using these two devices, you can calculate the fluid velocity. Next thing we'll discuss something called hydraulic grade line, HGL, and energy grade line. So this is called hydraulic grade line, HGL, and energy grade line. Anybody is aware about this term?
No, sir.
No, sir.
Okay. So whatever we discussed in the past, that is the same. If you have a piezometer, and then you can find hydraulic grade line, HGL. So what this means, so let us try to understand. So we have P by rho Z plus B square by 2Z plus Z, that is equals to constant. So this is your pressure head, this is your velocity head, and this is your elevation head. Pressure head, this is your velocity head, and this is your elevation head. So we define hydraulic grade line HGL is equals to P by rho Z plus Z. So this term plus this term, we will call this as a hydraulic grade line. So hydraulic grade line can be found by putting the piezometer at several locations along a pipe and drawing the line through the liquid levels in the piezometer. So how we can find hydraulic grade line? So let us write HGL can be found by piezometer by inserting the piezometer at several locations along a pipe and drawing a line through the liquid levels in the piezometer. So this is HGL is equals to Z plus P by rho Z. This means let us consider a something of this kind of pipe. So let us consider, and the water is flowing in this pipe, and this is my reference line. So this is my reference. So we define HGL is equal. So how we find hydraulic grade line? So what we will do is we will put different piezometers. At one place we put the piezometer and some height is coming. I will put piezometer at other place and then some other height will come. For example, if I put a piezometer at this place, water will rise up to this height. At this place, again water will, we are assuming there is no friction loss and anything, nothing like that. At this point, if we put the, this will. So if I basically join all these water levels, then the corresponding line will be hydraulic grade line. So this is my hydraulic grade line. Because your piezometers measures P plus this term, P by rho Z plus Z. And this Z will depend upon, Z is reference. So if you basically piezometer is measuring P by rho Z and you add a constant term, so this will be your hydraulic grade line. Now similarly you have a EGL, and this is defined as energy grade line. This is equals to P by rho Z plus Z plus V squared by 2Z. And this you can measure by putting the piezometer at different points. So at this point you put the piezometer, whatever the level of water here you have. Again you put the piezometer at this point and you find what is the level of water. And then join all these points, that is the level of waters, then the corresponding line will be called as energy grade line. Now the question is, what do you think? What kind of line you will get as an energy grade line?
A straight horizontal line.
A straight horizontal line. That's good, because this is a constant thing. So energy grade line will have that with a basically constant. So that's why we'll have a horizontal line. So in this case, if I plot the same figure once again, so if I put energy grade line, so this is my energy grade line. This will be a constant line. Now, this will be hydraulic grade line HGL, and the difference will be Vs square by 2Z. So here you have a Vs square by 2Z difference, here again you have a Vs square by 2Z difference. At some point you will have a difference more, at some point you will have difference less, because velocity is changing along the pipe, because cross section is changing. So ideally your energy grade line should be constant, a straight line, but in actual case, because of the friction and other viscous effect, the energy grade line is not horizontal in actual situation. Ideally it should be horizontal or it should be constant. Now some important point about energy grade line and hydraulic grade line. So the first point is, I can basically, what I can do is I can show these points and no need to write, I can explain. Okay, I can explain this even without going into the details, even without writing. So you see, is this figure visible to you? Is this
Yes,
figure
sir.
visible? Slide is like I have a figure here. Is that visible?
Yes.
Yes, sir.
Okay, good. So you see, in this case, this is your energy grid line. So this line, I have a fluid that is flowing through this pipe. So this is my energy grid line. And this is your hydraulic grid line, and this is the arbitrary reference. So there is a difference at this point, V1 square by 2Z, V2 square by 2Z, depending upon the velocity. The same thing here. Now some important point about these two lines. The first important point is, for stationary bodies such as reservoirs, lake, if you have a lake that is a stationary, water is not flowing, the energy grade line and EGL and HGL coincides with the free surface of the liquid. Makes sense? Because fluid is not flowing, this means velocity term is 0 and the difference between these two is 0. This means EGL and HGL will coincide. And also, this will coincide with the free surface. If you take free surface as the reference, both will coincide with the free surface, because Z is 0 in that case. You can basically say that if I take different Z is equals to different value, then again they will coincide, but they will coincide little bit up or little bit down depending upon what is your value of Z. So a stationary flow, a stationary objects, stationary bodies, EGL and HGL coincides with the free surface of the liquid. The elevation of the free surface Z in such case represent both EGL and HGL, since the velocity is 0 and the static pressure is 0. So elevation Z will basically denote both EGL or HGL. You can take Z is equals to 0 or you can take Z is equals to some value. So whatever that value is, that will represent your EGL and HGL. EGL is always a distance V square by 2Z above HGL. Makes sense because you have extra term V square by 2Z in that case. These two lines approach each other as the velocity decreases. So if we have a energy grade line here and hydraulic grade line here, the difference decreases if the velocity difference or basically velocity decreases. So these two lines approach each other as the velocity decreases and they diverge as the velocity increases. This makes sense. If you increase the velocity, these two lines will diverge, and if you make the velocity smaller, these two lines will converge. The height of HGL decreases as the velocity increases and vice versa. So this we explained. In an idealized Bernoulli type flow, EGL is horizontal and height remains constant. This would also be the case for HGL when the flow velocity is constant. So if flow velocity is constant, then HGL is constant, and EGL will be constant in case of horizontal Bernoulli type of flow. So whatever the assumption you have in the Bernoulli theorem, if you assume all this assumption, then EGL will be constant. If you consider friction or viscosity and other terms, non-steady flow, in that case EGL will not be constant. For open channel flow, so there are two terms that often comes. One is called closed flow, another is called open channel flow. What do you understand when I say open channel flow? Anyone? Give an example of open channel flow. Anybody?
Sir, river.
Yeah, good. So if you have a, if you have a flow that is inside a pipe, that is a closed flow, and if you have something like river or channel where water is flowing, surface is free, this is called open channel flow. So in open channel flow, HGL coincides with the free surface of liquid and EGL is at a distance of P square by 2Z above the surface. If you have a stationary, in that case V is 0, then both coincides. If it's not a stationary, water is flowing in an open channel, EGL is somewhere here and HGL coincides with the free surface, the top surface of the river or top surface of the open channel. And the difference between these two is V square by 2Z. At pipe exit, the pressure head is 0, atmospheric pressure, and thus HGL coincides with the pipe outlet. So if you have a pipe, the closed pipe, water is flowing through this pipe, atmospheric pressure at the exit, air water is exiting, the pressure head is 0, and if you assume that reference line Z is also at this point, then your HGL, so for example HGL is coming like this, but at the exit it will coincide with this point, because at this point the head is 0, pressure head is 0, because this is atmospheric pressure. So at exit point your HGL coincides with the outlet of the pipe, and in this case I am assuming Z, the reference, is also along the pipe or at the point of the exit of the pipe. Now often you have a pump and turbine you use. When we use pump, for example, if you want to increase the pressure inside a pipe or you want to flow the water for a long distance, then we use a pump. So pump provides energy to the water, and the reverse or opposite of that is called turbine. Turbine basically extract energy from the water. So if you have water that is flowing like this, and this is your hydraulic grid line, and this is your energy grid line, if you put a pump in this, there is a jump in the grid line. If you don't have pump and turbine, both will be like this. Energy grid line and hydraulic grid line will be something like this. But now if you put a pump in this case, energy will increase, the total energy will increase, and this will be the energy grid line. And similarly, hydraulic grid line will be this. If you put a turbine in the pipe, energy grid line and hydraulic grid line, both will basically decrease, and you will have something of this kind of situation. So we can stop here, and in the next class we will discuss more, and then after maybe next class and maybe 1 or 2 classes we'll discuss the dimensional analysis. If you have any doubt, then you can ask, otherwise you can log out.
No, sir, no doubt.
Okay. So I see like only 10 or 12 students or 13 students are coming. How many students were there? 13 or 14? I am not. Okay, I see here 17 students.
Yes, sir, so 16.
Okay. So generally, only this much amount of students are attending the classes or more? Or you don't find interest? it doesn't matter to me, like whether you attend or not. But you can watch the video lectures also if you want, or you can also follow any textbook. We can stop here, and I will see you tomorrow.
Okay, sir. Thank you.
Okay, bye. Thank you.
Thank you, sir. Okay, sir. Thank you.
Thank you.